Good afternoon everyone, I'm Yingli from Team 1 Cluster 1. So in this video, I'm going to present about the stability analysis of feed control system. In feed control system, you have unstable process and also stable process. So unstable process is the process when being disturbed and it doesn't return to the original value, while the stable process is the dynamic system is considered to be stable if every bounded input it produces a bounded output. So the stabilization of unstable process, you can see the equations is given in the yellow box, light yellow box. So the closed loop system with proportional controller, Gm equal to Gf, and both of them are equal to 1, it becomes the light yellow box equation become the dark yellow box equation. So for closed loop to be stable, Kc must be greater than 1 per 10, and the unstable process can be stabilized by proportional controller.
Assalamualaikum warahmatullahi wabarakatuh and hi everyone. Okay, about stability analysis of feed control system, I would like to talk about the stability analysis. As you can see, it have 3 points here. The first one, a given process is having this transfer function, which is, as you can see, the GP equal to 10 over S minus 1, which is GF equal to 1, GM equal to 1, and GC equal to KC. The second one is the corresponding characteristic equation is 1 plus GP, GF, GC, and GM equal to 1 plus 10 over S minus 1, and 1 plus KC, and 1 times KC times 1 equal to 0, which has the root P equal to 1 minus 10 Kc. The system will be stable if P less than 0 and Kc more than 1 over 10.
So for the Rough-Hurwitz stability criteria, the criterion of stability for closed loop system does not require the actual values of the roots. It only requires the roots to be on the right of the imaginary axis. So we have to expand the characteristic equations in the form of polynomial, and the equation is given in this light green box. Then we have to let the a0 to be positive, or else we have to multiply the both sides of the equations with -1. In first test, if any of the coefficients 0, a0, a1, an minus 1, an is negative, means that there's at least one root is positive. While if the order of the coefficients is missing, or the order of coefficient is 0, it means that the process is not stable. So the corresponding system is unstable and no further analysis is needed. While in test 2, if coefficients a0, a1, an minus 1, an are positive, then we have to form the rough array, which is the formation you can see in this light yellow box. So the equations of a1, a2, b2, b1 is given at the sides of the light yellow box. Yeah, that's all from me, and thank you, and I will pass to my other teammates.
Good afternoon, I'm Sharmila from Team 1 Cluster 1. So today I'm going to present about the selection of controllers. So under the selection of controllers, we have 3 main types of controllers, which are proportional controller, PI controller, and also PID controller. So when it comes to the proportional controller, it can achieve acceptable offset with moderate value of Kc, and the process has integrating factors. So the function of proportional controller is actually to control gas pressure and liquid level. And then for PI controller, it will be used whenever we cannot accept small steady state error, which is the offset. So this PI controller will be used when the response is fast, and the function is to control the flow. Lastly, the PID controller. PID controller increases speed of closed loop response and retains robustness. So it is suitable for multi-capacity whose response is sluggish, and it is recommended for temperature and composition control.
Okay, for the next part, I would like to talk about the effect of controller's mode. The first effect is proportional mode P. Make the closed loop respond faster. Having offset as set for pure capacitive process. And for integral mode, no offset, having bigger deviation when the process oscillates. The response is sluggish or having long oscillatory. When Kc is increased, the response becomes oscillatory and can lead to stability. Okay, for the last one, derivative mode D, able to predict the future error and take action accordingly, giving stability to closed loop response. When the error is constant, the controller do not functioning. Okay, for the last one, I will talk about general stability criterion. The feedback control system stable if and only if all the roots of the characteristic equation are negative or have negative part. As you can see in this picture, it has stable region and unstable region. The exists for imaginary parts and real part. The first one, negative free root. As you can see, the graph, and the second one is positive real root. The third one is complex roots, negative real parts, and last but not least, complex roots, positive real parts. Okay, we move to the assumption for the criterion. The first one, set point rather than disturbance change were considered. Second loop, transfer function was ratio of polynomial, and last but not least, the poles in equation 2 are distinct. That's all from me.
Next, we move to Cohen-Kuhn technique, and this is the normal graph of variables over time. And firstly, we need to do this loop to find the time delay theta and find the tau and also k. And there are several equations based on the controller to find the Kc, tau I, and tau d. And here's the equations. And it is similar for Ziegler-Nichols open loop formula, where it has its own formula to find Kc, tau n, and also tau d.
Okay, now I'm going to explain about the first order plus time delay model, which is also known as the FOPTD model. So consider the standard first order plus time delay model, and we have two main equations, which are g is equal to k e to the power of negative theta s over tau s plus 1, and then the second equation is gc is equal to 1 over g bracket e to the power of negative theta s over tau c plus theta bracket s. So these are the two main equations, and we have to substitute the first equation into the second equation, and then we have to rearrange it, which will give us the PI controller equation. So the PI controller equation is GC is equal to KC bracket 1 plus 1 over tau 1s. KC is actually the controller gain. So the expression for KC is equal to 1 over K tau over theta plus tau C. And this expression is for the PI controller settings, and it will provide considerable insight. So the controller gain depends inversely on model gain, which is reasonable based on the stability analysis. So I think that's all from us. Thank you.